All right. Hi, everybody. Happy Wednesday. Welcome to our 5-able AP Physics 1 open Q&A, anything test-related, questions go, sort of stuff like that. My name is Peter Epps, and I will be going through quite a few different topics so far. If you guys have questions or a topic you want to see me cover, please either use the Ask a Question button or throw up your request in the chat, and I'll do my best to get to it in the order that they're received, pretty much on there. So plan for today. Today is Wednesday, so it's Science Day. We also have another test prep Physics 1 stream going on at 7 o'clock tonight. And then the same thing on the 13th. We will do pretty much open test prep for those things as well. If you're a cram session pass person, if you bought that, there's also a mega test prep stream on the 13th, the day before the exam, that'll go from 4 till 9. So that will be a major chunk of time devoted to your questions. We have, I think, 3 or 4 different speakers coming in, all people who've done well on the test before and doing that for the cram session. So just to plug that as well. And if you're not a cram session person, there'll be the normal 1 hour 7 till 8 stream that Wednesday as well. Okay. Yeah, I think 5-ball. So the plan for today, open Q&A, everything goes. These are the topics I've already got requests for, so we're going to kind of hit those in order there. And then, again, if you guys have other questions or want to see more work on one of these things, please just let me know, and I will do my best to get that done. All right, so that being said, I'm going to switch over to my notepad for a second here. So please bear with me as I make this transition. Okay, and there we go. Perfect. All right, so this was the first request was for some sort of conservation or momentum question. This one, I made a 2D one because if you can understand 2D, it's the same thing as 1D. This was just a little bit more in-depth going on here. So this is an old AP question, and we basically need to understand the concepts behind it. The math, I'm not super convinced you're going to have to do a ton of math on this year's exam because it is just 2 questions with essays. But we've got numbers here just in case as well on there. So we got 2 objects, M1 and M2. They're moving on a horizontal frictionless surface, and they collide with each other. Okay, so M1, M2 beforehand, and then afterwards they collide at some sort of angle. Normally, when we see momentum questions, we're talking about one direction. This one's dealing with 2. It's no different. All we have to do is worry about what's happening in the vertical sense and what's happening in the horizontal sense. So before the collision, mass M1, this guy right here, is moving at a speed of 16 meters per second and has a mass of 1 kilogram. So its momentum, remember, P equals mv. So its momentum beforehand is 16. In the y direction, it's not moving up or down. So it has no momentum in the y direction. And of course, our second mass, the 4 kilogram one, isn't moving. So it has no momentum before or after the collision either. Sorry, before the collision. I haven't looked at after yet. Afterwards, we have M1 now moving entirely in the y direction. So its momentum is going to be negative 12. Negative because it's going downwards in that negative direction, and 12 because 12 times 1 is 12. And not moving at all in the horizontal direction. For the bigger mass, the M4, it's now moving at a 37-degree angle. So some part of its motion is in the x direction, and some part of its motion is in the y direction. All we have to do is split it up now. So its momentum in the y direction will be 4 kilograms times 5 meters per second times our trig function to go vertical. Now, vertical is opposite the 37-degree angle. So we'll do sine of 37. Okay, so we take the momentum, and all we're doing is finding the vertical velocity instead of the total velocity in there. So 4 times 5 times the sine of 37. They tell us the sine of 37 is 0.6. So that gives us a 16 when you plug that in the calculator, or really close with actual rounding here, in the x direction. Now for the that was the y direction. I can do math. That is 12 in the y direction. And the x one that I already did the math for, 4 times 5 times the cos of 37. This is 12. This is 16. So we get this table filled out kind of like that. That's a terrible 6, but it will work. Now we're asked to do, so we fill out the table, we found momentums and all those things. We're supposed to show that linear momentum is conserved. So conservation of momentum, we should be able to say for part B, P before in the x direction equals P after in the x direction. So yeah, I would go through and now basically, okay, so beforehand would be 16 plus 0. Does that equal, so I'm adding the px before and the px before for both m1 and m2. Afterwards, I have 0 for mass 1, and I have 16 for mass 2. 16 equals 16. That one checks. And we should also be able to say the same thing for the y direction. Momentum before in the y direction should equal momentum after in the y direction. Tablet's being a little screwy here. So I have 0 beforehand plus 0 beforehand should equal negative 12 plus 12. 0 equals 0. That one also checks. So we have conservation of momentum in both the x direction and the y direction, so it's conserved overall. Okay. Now, if you get a question, and this doesn't just apply with momentum, we can do it with projectile motion or something like that too. I would strongly encourage making some sort of table with an x and a y column, just so we don't get stuff mixed up. It doesn't have to look like this example. It can be just a simple, here's the x, here's the y, and then go from there. But strongly recommend splitting it up into some sort of table, just so it's easier to read and keep track of your variables and stuff like that in there. Okay. Part C asks for the kinetic energy before and after. Okay, so kinetic energy. What do the no solution signs mean? Okay, are you talking about my equals 16 sort of thing here? It just means they're equivalent to each other. I'm trying to prove that the momentum was equal before and after. So I found the momentum side and I found before and after. Sorry, yeah, 0 with a circle. Sorry, yeah, I slashed my zeros so to make it not look like an O. So yeah, 0 with a slash through it is 0 on there. Okay, part C, kinetic energy before and after. Beforehand is just m1, so that's 1/2 1, and it's moving at 16 meters per second squared. So that's my before. Kinetic energy after. Now I've got 2 objects, so I've got to add them both up. So that's 1/2 of 1 times 12 squared plus 1/2 of 4 times 5 squared. I don't care about x and y. We're talking about energy, so I can just use the 5 as the velocity after the fact on there, and we'll get our numbers. In this case, let me crunch the numbers here. 1/2 12 squared is 144. So we're doing 144 plus, let's see, 0.5 times 144 plus 0.5 times numbers. 25 times 4 is 100, so 100. There you go. And this will give us an answer of 122 joules. And then if we compare it to 0.5 times 1 times 16 squared, you end up with 128. Oh, is kinetic energy conserved? Nope, it's not. We don't have the same energy before and after. Okay, and those are basically the solution to this part of it. So we go through, we figure it out, we crunch the math. So because kinetic energy is not conserved, the buzzword for this would be inelastic for the collision. Okay. So I wouldn't describe it as perfectly inelastic now. I would just call it inelastic. I'm not going to worry about definitions beyond that. And if it comes up on the exam, they're going to ask you, is it elastic or inelastic? So this one's definitely inelastic because the energy is not conserved. But I would call it partially inelastic. Completely inelastic to me is when it sticks. When you have two objects stick together and become one, that's perfectly inelastic or completely inelastic. So I would call this one just partially inelastic in there. Why does momentum show up so often? Momentum is a great one that lets us tie different concepts together. So with momentum, we could do an energy question, like we brought in energy here. You can talk about velocities afterwards and bring in kinematics. You can talk a little bit about forces and impulse and stuff like that and bring in forces. So momentum is one of those kind of shell sort of scenarios that brings in a lot of other topics in here. So that's why momentum, you'll see this with momentum. Simple harmonic motion is another one that tends to bring in a bunch of other concepts that makes it really good for a justify your answer or a qual-quant sort of problem like we're going to see on this year's exam. So that's why it shows up a lot. Not because it's super important, but because we can do a lot with the momentum and energy and velocities and forces. It all just comes together really well. Carol, how do I know energy is not conserved in this case? I know it's not conserved because I got my total energy before the collision to be 128 joules, and afterwards it's 122 joules. They are not the same number, so we do not have a conservation of kinetic energy. Therefore, it's an inelastic collision. Total energy, if we look at the entire objects, overall it's conserved, but that energy goes into heat or thermal or sound or something like that we just don't keep track of. So when we say inelastic or elastic, we're talking about just kinetic energy being conserved, and that's why it's inelastic in this case. John, is there any way to predict what happens after a 1D partially inelastic collision by just knowing the masses and initial velocities? You would need to know either you have to know one of the final velocities. Or they could tell you that it is elastic, and that way you can use kinetic energies to work that out. So either you need to be told that it's elastic, in which case you've got P before equals P after and energy before equals energy after as your two equations, or they have to tell you one of the final speeds or something about the final situation on there. So that's definitely doable on there. Yep. Okay. Any other momentum questions before we move on to our next sort of shindig here? Okay, so what if we had a ball that bounced off a wall at an angle and it asked for the change in momentum? Okay, let's do one. Let's make a new one here. So I'm going to have my wall. We've got a ball. It's coming in and it's bouncing off. And it hits at some angle. Let's call it theta. Okay, so it comes in and goes out at the same angle, just for simplicity here. Goes in at some speed. So this is mass m, speed v, and this comes off at mass m, speed negative v. Let's just say, or something like that. Yeah, some speed v. So we're not changing the speed, we're just changing the direction it's going through. In this case, we would have to, again, look at two directions here, because we have this ball moving both in the horizontal direction, so moving horizontal and vertical, and then vertical and horizontal. Okay, so in this case, we can say something like the change in momentum in the x direction will have to be something, and then the change in momentum in the y direction is going to be 0 in this case. We're not going to change any momentum vertically. We were going upwards at the beginning with some, what is this? This is going to be this side opposite the angle, so this will be v sine theta. And then at the other end, we would still have v sine theta for our velocity going in there. Now, I wouldn't in this case. We just worry about, in this instant, this is what's happening. The question is telling us we have the same velocity going in and out, or the same speed going in and out. Let's not overcomplicate it by trying to worry about gravity and other stuff like that in there. It's not going to be useful in this case. Okay, or at least we can talk about the time scale is so short, we're not worrying about it arcing down and stuff like that. In there. So in this case, we have v sine theta, the same velocity in before and after, and the same mass doesn't change. So the vertical stuff doesn't change at all. In the horizontal one, we would have this be v cos theta, and in this one would be, let's say, negative v cos theta. Or you can switch the negative around. One direction has to be positive, the other one has to be negative. So in this case, it's going to be equal to, the way I have it drawn will be negative v cos theta minus v cos theta, or negative 2 v cos theta for our change in momentum in the x direction. So, and again, that negative sign just means direction. You have the freedom to choose that other part like that. So you basically have a double the change in momentum going in there. Meg, the question was just about how do we do change in momentum for something bouncing off a wall. So we were looking for basically this change in momentum that in the x, it changes by that much, and the y, it changes by nothing. Looking at 2 dimensions in here, doing some trig to figure out the speeds in each direction, and then mv, actually, I should put an mv in there. Let's put m's in there, make it momentum, not just v's. Good catch, Carol, just did. Yep. Yeah, so that was just the velocities here. We'd have to put the m's in there. So put an m times that and m times that in there. So, yep. Yeah, and if you do it as a different angle, all you're going to do here, it's still a change. So it's still final minus initial. So if these were not the same angle, so let's say this was, let's say, a 45 and a 30, just for the sake of, you would then have to say that we are changing momentum in both the y and the x. So in this case, this would be Vx would be V cos 45, and then Vy would be V sine 45. And then the same deal here. This would be Vy would be V sine 30, and Vx equals V cos 30. And then all you would do is change momentum in the y direction will be the mass times V sine 30. Boy, come on, pen work. Minus m times V sine 45. And then you do the same thing for the delta x's in there. So splitting up in those things there. Yeah, it's a bit more trig, but it's the same basic idea. The way I teach it to my kids is you always just look what's opposite the angle. If it's opposite the angle, you're using sine. If it's adjacent to the angle, you're using cosine. If you got a question like this, and I'm not expecting a question like this on this year's exam, doing all the math, I would see them doing something like, hey, you're bouncing off versus sticking, which one has a bigger change in momentum? And the bouncing off one does, because you're going from a positive momentum to a negative momentum, something like that in there. So yeah, it is more trig, but it's also not a ton. You guys also have a wonderful calculator you get to use on this exam. Not that I'm expecting you to need it, but just plugging that into your calculator and giving it a V, go from there, is also perfectly doable. So there's another example of bouncing on there in 2 dimensions, breaking it up into the x and the y and going from there on that part. All right. Other questions on this one? Are we good to move on? Now, so it depends. With my first example where you had both thetas being equal to each other, all your delta y, or your momentum change, was in the x direction. So you can just say delta p equals negative 2 v naught cos theta in the x direction or something like that. For the case where you had 2 different angles, I'd probably do delta px and delta py. You could also Pythagorean them together. P squared equals px squared plus py squared, and get a total change in momentum. It would really depend on what the question would ask for. But again, I'm thinking about this as for this year's exam specifically, you're doing much more qualitative stuff. So it'll be compare what's going on. And if you want to justify it with some math, there's the math for it. But I'm thinking more about rank these 2 different things in terms of it. Yeah, quality is definitely better than quantity in there. So if you're doing an explanation or doing the math out, you want to do it right, but you don't also want to get bogged down in so many of the details that it takes you forever to write these questions. Remember, you're given 25 minutes for one of them and 15 for the other, I think. And maybe that's close to what it is, 45 minutes overall. So don't get bogged down writing pages of worth of stuff. These are meant to be paragraphs or short sentences, sort of stuff like that. Proving your point, justifying your point. But don't get worried about having pages of pages of pages of stuff. Quality is definitely better than quantity. So how picky are AP readers? It's kind of funny. You're going to get one person typically at a table who will be a super stickler about saying, well, you know what, I used V for velocity here, and that really should be speed, so you should use S instead. The majority of us, when we're going to read these, we want to care about, did you understand the physics? Did you show us what's going on? So because I messed up calling speed velocity, I'm not going to penalize you a ton for that. Unless the question specifically is getting at, do you know the difference between speed and velocity? But in a general question like this, if you talked about the horizontal speed versus the horizontal velocity, who cares? Or angular speed versus angular velocity, I don't care. You're talking about some rate in that given direction that's going to be good enough for me. Like I said, unless the question's really getting into a difference between speed and velocity. Like if you talk about a negative speed on an equation or on a problem that's going to get at the fact that velocity is negative, but speed's always a positive number, then maybe we'd have an issue. But in general, you prove the physics right. And as long as you're close on terminology, we're good with it. Yep. Yeah. As much as we're going to be doing writing for this exam, it's not an English exam. So as long as you are doing reasonably good with speed velocity or stuff like that. I will be fairly picky as a reader about, I think we've talked about this in previous streams, energies. Like if you're talking about kinetic energy, tell me specifically, is this rotational or is this linear? Or if it's a projectile motion sort of thing, be sure you're talking about horizontal versus vertical, and don't just say the word speed and expect me to figure it out in there. So clarify when you can, but don't get hung up entirely on the nitpicky details in there. Yeah, when in doubt, be specific. If there's a reason that somebody will be doubting about it. Like if I'm talking about momentum, I'm not going to do a whole paragraph describing, oh, I'm defining the positive momentum to be in this direction, and this means that, and this means that. I'm going to say, hey, the momentum is, or the energy is. If it's a question where I have to break down total energy versus PEG versus PES versus KE rotational versus KE linear, then I'll take the time and be extra specific about those sort of things. Okay. When we are asked to derive speed, do we go conservation of energy? And when we go to, when do we do conservation of energy? Okay, so let's talk about conservation laws in general here, and when we can go to them or not. So let me make a new page here, new page. All right, so in general, conservation of blank. Okay, first off, when we're talking about conservation of energy, we have to make sure that there are no external forces or torques acting on our system. Okay? So this would mean that whatever system we're defining, all the forces that are going on are happening internally on there. Only conservative forces? No, actually, it's any force going on there. So for example, if I'm talking about a ball falling, if I define my system as just the ball, there's an external force, gravity, acting on it. And that even though gravity is conservative, or the force of gravity is conservative, that would still be an external force, not included in my system. If I included the system as the ball and the earth, then all the forces are included in there because gravity is caused by those two objects interacting. That's an internal force. So the ball by itself, I have unbalanced forces. I can't do conservation of energy. The ball earth system, I have all my forces internal, no external, and I would call that to be conservation of energy. Friction, if friction, it depends on what my system is. If I wanted to, most of the time we ignore friction, like air resistance, stuff like that for that falling ball, we wouldn't care about it. If it was a block on a friction surface and I want to talk about the energy of the block, I might say friction's an external force. If I want to include it in the whole thing, the block, ground, earth, rough surface system, I can say that I can do conservation of energy, and I would do like kinetic energy of the block turns into internal energy in that system, instead of saying friction did work and made it lose. Okay. So John says, if there's an external force that's balanced by an internal force, could you use conservation of energy like a book hanging from a string by a tree where the system is defined as the book in the earth? Well, in that case, if there's balanced forces, there's no changes in energy going on there. So again, there's no work doing done. There's no outside sort of stuff going on there. So I would just say, sure, you could, but what's the purpose of doing conservation of energy there? Yeah, I would either do forces or do energies in that case. So going back to the question above here. So now I've shown that there's no external stuff going on here, and we're supposed to find other things we're doing. So typically, if we're looking at the words collision, I-S-I-O-N, that's going to clue me into I got to use momentum. Whether it's angular or not. Anytime they talk about colliding or running into or stuff like that, I'm going to use conservation of momentum. If they give me M's, V's, heights maybe, or a K value, then I'm definitely getting into energy for that case. Just looking at the different options I have to work with in there. So if we're asked to find speed on a frictionless surface, like I'm pushing on a block, so doing something like this where I have my block and I'm pushing on it with some force F, and they want to know, let's say they give me a distance to move here and they want to find the velocity at the end. Sure, I can do work. So this could be a work equals force times distance equals change in energy sort of question. So this would be F times X equals 1/2 mv squared minus 0 because we weren't moving at the beginning, that sort of question like that. If they added friction in here, whoa, I don't want to type, go away. If they added friction, going back in, done. I don't want to type anymore. What just happened here? Forget it, we'll use this computer. So if I wanted to add friction going back the other way as another force going that way, all I would do here is simply say that, okay, this is really, really irritating me. All I would do is say that, let's not do that question. I would have this be F minus the force of friction in there. Although you could also have done anything with energy or stuff like that in there. That is perfectly fine to do as well. All right, let's see if I can get that back up and working. So with this question, if they give you a rough surface with friction and they want you to do a bunch of stuff on there, you could do energy if you know the distance. So you can do work equals FD equals delta E. You could do Newton's laws, F equals MA, and some kinematics. That also works perfectly fine in there. Use the net force to find the acceleration, use the acceleration and the distance to find the final velocity. So both those things are both workable in there and such like that. So it kind of depends on what you're comfortable with, what feels best in your wheelhouse, kind of out of the big topics that we can work with. So again, if you want to talk big topics, these are the ones that I typically tell my kids. If you don't know where to start on a question, and these are kind of the go in order sort of options here, I would start with first off. Okay, so one, I always tell my kids, let's try forces first. Am I talking about F equals MA or something along those lines? If that doesn't work or you're not told forces, let's try energy. Okay, can we do some sort of work equals total energy, or PE turns into kinetic energy, something like that? Can I get into that sort of thing? If that one doesn't work, or you don't feel enough to do energy, maybe this is a momentum. Am I talking about a collision or something crashing together? If I'm not seeing the word collision or impact or stuff like that in a question, I'm not doing momentum. Number 4 would be some sort of rotational sort of question. So am I doing angular stuff or moving around or things like that? Generally, those are going to be either forces, or I should say torques, or energy in there as well, depending on what the question gives you. And then finally, projectile motion. I suppose I'll put simple harmonic motion on there as well. Other part with SHM, the reason I put it at the end is because most of the SHM questions you're going to see are going to be solved with forces or energy or rotational stuff. And really the only one that just comes down to pure simple harmonic motion is the period part, the period of a pendulum, the period of a spring, sort of stuff like that on there. And then this would be pneumatic sort of stuff. So those are my big 5, 6-ish sort of things that I would have my kids, if you don't know where to start, kind of go in order of those things. Most of the questions we're dealing with are going to be F equals MA on there, and then we hit energy and the other things like that. Okay, what's next? There's a question about rotational rolling without slipping. Okay, let's do some rolling without slipping and see where this goes. Okay, so let's do a very nice, make my screen the right way. There we go. So let's say we have a ball. Let's do it on a ramp. Let's do some energy stuff there as well. So I'm going to draw a ramp with a ball. This ball is mass m. Moment of inertia, we're to make it 1/2 mr squared, just to make it easy here. This distance we will call h. And yeah, we can go from there. So there's basically a couple different ways they can do this. They can talk about this ramp having friction or not. If we don't have friction, we can just do simple potential energy turns into kinetic energy, go from there, right? We can say PE G turns into kinetic energy and go. This is no friction. With friction, we have to talk about, okay, we still start with potential energy due to gravity, but now we have some sort of rolling. Friction is going to make a torque. It's going to act at the bottom of our sphere. It's going to be pointing perpendicular to the radius, which means force of friction gives us a torque, which means we start rolling. Okay. So this potential energy due to gravity now just doesn't turn into linear kinetic energy or translational kinetic energy. We get rotational kinetic energy plus translational kinetic energy. And this is where you could do things like mgh equals 1/2 I omega squared plus 1/2 mv squared. Plug in some stuff and kind of go to town on that sort of thing. So for no friction, that KE is definitely translational. There's no way you can roll. Without friction, we don't get any sort of rolling motion. All you get is sliding on there, okay? For the with friction part, this thing is still going to move sideways. It'll still have some velocity as it goes down there, which is why we still have translational kinetic energy in that case. But it will also be rolling with some angular velocity omega, which means we have some rotational energy in there. So with friction, we get some of that energy that would just be pure sideways, pure translational motion, and it gets converted into rotational in there. And then we can crunch the numbers and do the math here if we felt the urge to do it. All the m's drop out, the 1/2s come over there and stuff like that on there. So yeah, that's where we're getting the rotational part out of it, because we are rolling, so kinetic, rotational kinetic energy, and moving sideways, so translational kinetic energy. Okay, and then ... on the math. You guys can take it from here. It's solve and go and stuff like that. There is the one equation here, the V equals omega R. Can I make an omega? There we go. That absolutely needs to be written down on your cheat sheet, on your notes page, on your sort of stuff like that when it comes time for the exam, if you don't have it memorized already, because that is one that definitely needs to be put on there. All right, Sophia, there was a concept I saw in a video a while back. I didn't get a bicycle wheel, and the teacher said that at a certain point P, which is at the bottom of the wheel, the net force is 0, while the top of the wheel has a net velocity or something like that. Okay, so I think what the teacher's trying to get at there is if I look at a wheel on a rough surface, okay, so some sort of surface here that we are rolling around, and let's assume we have a constant velocity here just to make it easier. So we have nice uniform circular motion going on. At the bottom of the wheel, you have some tension or torque or something like that. Actually, let's do this as a spinning something around in a circle. At the bottom, you have tension and gravity of those objects. And while they shouldn't be 0, this part, these actually, we should have tension be bigger than gravity, because we need to have that upwards force going on there. In there, if you don't have an upwards force, you shouldn't have a net force be 0 on there. At the top of the wheel, you've got them working together to make it rotate around more and stuff like that. This is a wheel, or it doesn't really matter. You can do a wheel, you can do something spinning on there. Both ways work on that case. The part from the video probably is saying something like talking about why is there tension? It would be some sort of internal force. If it's a wheel, it's the tension from the spokes or stuff like that in there. Normal force would work too. Yeah, I'm mixing metaphors here. Tension would work if you're spinning. Normal force would work if it's a wheel, stuff like that on there. The key part here, though, is as long as you're rotating, you will never have a net force be 0 in the rotating sense. Now, if this wheel was accelerating and stuff like that, then you could have a net force that would be changing throughout here. But here, remember, in order to be rotating constant velocity, you have to have your mv squared over r sort of thing going on there. Why wouldn't there be a normal force? There would be if it's on the surface. I'm mixing two different options here, so let me clarify. If you had this not a spinning object, then yes, you'd have a normal force going up and then no normal force at the top. If this was an object spinning in a circle, you would have tension and then gravity and tension, that sort of thing. So this was roll. This was, this was wheel. And this was spin. It's the same basic idea. All we're doing is arguing over which force is named. The idea there is there. So, all right, going back through some other questions in there. Do we need to work with potential energy versus difference graphs, like knowing the slope of the force? I have not seen any examples where we have to do potential energy graphs. I have seen quite a few examples where, for example, we have to do a question like this, which is dealing with force distance graphs. And then knowing on that the area of this, which is force times distance, that equals the work of the object. So we've definitely seen questions like that. I haven't seen any that flip it around and expect you to do the slope of a energy distance graph is force on there. I haven't seen any questions like that. Okay, what equations do we need to know for SHM? Okay, and then the table inside a book on top of a table. Was there a force of friction to the lowest position? Is there an F? Interesting. I'll ponder that one for a second, Dan. I don't have a good answer for that one right at the beginning here. For simple harmonic motion, basically the stuff you need to know. Doing it real quick. You need to know your period stuff. So looking up the period in pendulum and spring, sort of stuff like that. You need to know how to do energy and apply it to that specific position. So for a pendulum, it's potential turns into kinetic, turns into potential. For a spring, it's potential energy in a spring. I'm sorry, a horizontal spring. PES turns into KE, turns into other stuff like that going through. And then you probably also want to know your F equals MA stuff, and then acceleration, velocity, position, your sort of graphs. Like your acceleration will be 0 at the equilibrium, then go up high and down low and around, stuff like that. So this would be the extreme. That's your X. Your velocity graph would start off moving fast at the equilibrium position, down to 0, back up, kind of like that. And then your acceleration will be pretty much the same here. It's going to be, in this case, we're slowing down, so -0, up and 0 again. So that sort of stuff, knowing how your graphs and stuff like that go through. Yeah, so the College Board one. For simple harmonic motion, if you haven't done rotational stuff, does angular stuff and rotational stuff kind of play at first? No. Not normally. Most of the simple harmonic motion I have seen and questions that are out there are not dealing with rotational sort of stuff in there. You could definitely do rotational sort of stuff, but it's more, the ones I've seen, the ones I give my kids are period, energy, forces, and then acceleration sort of stuff like that in there. Yeah, I haven't watched that College Board YouTube video, but let's see if we can figure it out here. So we have an amusement ride with a table inside and a book on top of a table. I'm guessing, is this going around in a circle? It's got to be right, because then you said lowest position in there. Yeah, so in a circle. So we have some sort of spinning around a vertical circle. Vertical or horizontal? Hey, there's a link. Let's see if I can find it here. Sample questions. This one, oh, okay, here it is. Snippy, snip, snip, snip. Okay. Grab this for a second here. Snipping tool, new snip. Grab and go. Okay. Copy, bit paper. Let's delete this one. We'll start again. Yeah, go ahead, go away. Let's make a new one. Let's paste it in there. Okay, let's see what we got. So we've got all this stuff here. Okay, forces at the lowest point, et cetera, et cetera, et cetera. The lowest, okay, so there's all that stuff like that. And then the question basically goes on to say, and this is the part I think you guys were getting into here, at the lowest point. Okay, so students are arguing about which one is right about this. So there's that, and then there's the argument part. Okay. Yeah, I haven't actually seen these questions before. These are pretty good. All right. So the book's moving on in the horizontal direction, the force of friction acting on the book. Okay. So what they're saying here is you're looking at the book. And again, so the book here right now will have a couple of forces acting on it. All right. It's got to have some sort of normal force. It's got to have some sort of weight going down. And in there, it says the velocity is moving towards the right. Yeah, so we have a velocity, again, tangent to our circle, going sideways. All right, so students are arguing about this thing. At the lowest position, the book experiences no force of friction at all because the net force is only in the vertical direction. Okay. Student 2, force of kinetic friction because the whole thing's moving to the right. And then 3, a force of static friction because the book doesn't slip relative to the bench. Okay. These are all reasonable answers on here. Now, I'm going to preface this by saying I have not looked at this question a ton, so I may say something stupid. This is not one that I prepped with this. But my first thought, looking at this, if I look at the free body diagram on the book, we have an up force and a down force going on here. There is no acceleration between or no horizontal acceleration at all in this case. So what that's telling me here is we have basically some sort of circular motion. I forget, did it mention that we had a constant velocity in here? Yeah, constant angular speed. So we have a constant omega in there. Okay, so constant angular speed, super UCM. So we are really talking about UCM here. Constant circular motion going on. My first guess is to say student 1's right. There is no horizontal acceleration at all here at the lowest point. So because it's at the lowest point, all those forces are acting completely vertically on here. Goes in there. So I'm tempted to say student 1 is good. Student 3, the static friction because the book doesn't slip relative to the bench. Yes, it doesn't slip relative to the bench, but what's the force friction has to overcome? There's no sideways force acting on that book, period. It's not that the bench is being pushed sideways and the book stays in place on top of it. Right, so the book is moving in the horizontal direction, but that doesn't mean that it has a force in the horizontal direction. Okay, so I guess my point with this would be like, hey, if I have these two blocks stuck together and they're moving with a speed to the right, nowhere in there, or to the left in whatever case we're moving here, there's no point in there that says I'm pushing on them. This could be two things sitting on top of each other, sliding on the ice together. And as long as those forces are, no one's pushing harder on it. This isn't me pulling hard with a force on the bottom book and then suddenly saying, why does the top one not, or what, I'm not yanking on the bench at all. Stuff like that going in here. If this was a horizontal circle, I would say, sure, there's got to be some friction going on because that would make it move in a center of a towards the center of the circle. But our force here is going just upwards. The normal force is providing the centripetal force. I don't think we need anything acting sideways in this case. And if there was static friction, you'd have to have a force opposing it to keep that book from not accelerating off the bench and stuff like that. So my argument, I guess I'm arguing for student 1 here. Carol, I'm saying there's no horizontal force that friction has to oppose. This is saying we have a constant velocity going on here. So yeah, I'm really interested to see now what College Board would have said for their answer, because mine is, I'm definitely arguing, I'm thinking student 1 has a really compelling argument here on there. Student 2, I don't like student 2 in here. I don't like student 2 because if it was kinetic friction, the book would have to be sliding on the bench. And that is not what's happening here, right? Nowhere in this question does it say the book is sliding back and forth in here. So student 2, I don't like because of sliding. Student 3, like I get what you guys are saying. We have static friction going on here. Because if there was a force pushing the book to the side, you would have static friction going on. But I don't see a force going to the side. I see just two forces, an up and a down, going on there. And because they're talking about constant angular speed and constant velocity, or sorry, constant uniform circular motion, constant speed, constant angular velocity, that sort of stuff like that. I don't see anything that says it goes in there. Where would the static friction come from? The static friction would be between the book and the bench. So the surface of the book and the surface of the bench are not perfectly smooth. They would have some friction in there, which would be like if I were to grab that bench and move it a little bit, and accelerate it a little bit, the block would probably still stay with it, because it has static friction holding it in place and keeping it going in there. That's where I think they're coming from in there, is that because the book is not flying off, there must be static friction. I think my point is you don't even need static friction in order for this thing to keep going through. No, if I look at the entire system, if I want to look at this entire object as one large system going on there, the only force I need for it to keep this thing moving in a circle is an upward net force on there. If I look at just the book and then say, okay, now I need to accelerate the book in a circle, it still needs to have just an upward net force on it. If there was no friction, I think the book stays right there because there's no forces acting on it sideways at the lowest position. If we were somewhere else in that loop, let's say if we were over here at one of these sideways positions, absolutely you need friction, because friction is what's going to point that towards the center, and that's what's going to actually keep this thing accelerating in a circle. But at the bottom, I don't think there's a need for friction. All right. So yeah, that's my thought on it. I'm really interested in seeing what the College Board would say about that. Did they give an example? No, that's another one that I stole. Okay. Yeah, very interesting. Yeah. I'm going to have to go look at YouTube and watch that video. Let's see. They didn't post an answer key on there, did they? I don't think they would have, but. Notes and practice problems. It's old. It's 325. That's not the right one. Which one was this? This was the May 6th one. Okay. And is that live now? Looks like it's live now, isn't it? Or will be live. That's 7. That's yesterday. This one. Let's see. Did they bother to they put it in there? Be interested to see if they.
Good afternoon and welcome.
Whoa, that's not the right one. Pause. Sorry. Yeah, very interesting. No, so if you just, for most of these, if you justify the question correctly, you can still justify a wrong example and be fine with it. In there. So you can definitely go through and be okay explaining a wrong answer and still get points for justifying with good physics. But you can also, now if this was simply a less than, greater than, equal to sort of question, sometimes you can't get points for that sort of thing because they're really just making sure you check the right box. But for anything where you're justifying or arguing with the student, you can get partial credit for that easily. Okay. So since there's no external forces acting on the book, there couldn't be any state of friction. So I guess if you look at the book, there will be cases where there will be static friction acting on the book. Those cases are where you need to have a force point horizontally for some reason, like at the edges of the wheel. The edges of the wheel where it points in towards the center, or actually anywhere other than the top and bottom, that will make it have a force of friction on there. Otherwise, you shouldn't need it in there. All right, now can we do a question with work? Sure, let's grab one with the work. Do you want to do work into energy or just work as force times distance? energy. Okay, so yeah, let's do. Okay, let me find a blank page here. All right, so let's just do a. That's not the right one either. Come back here. One more page down. No. This one. Okay. So let's say we have. Let's just do a box. Okay. No, let's do rolling down a hill or something like that. No, I want to do. Let's do this. Rough surface, box, mass m. Starts off with velocity v. And then at some position here, we will say, let's say its velocity is now v1. It is less velocity than before. So v1 is smaller than v0. Okay. And this distance was covered by some variable. Let's call it x. And we're asking just what was the work done by friction. Actually, we can take it a step further. Let's find mu. Let's find the coefficient of friction between these two objects. Okay, so we have this box going on a rough surface over a distance d, and it slows down, and part of that there. Now, yeah, do I want to go any further? We'll leave it as right now. You may see cases where v1 becomes 0 or comes to a stop, but this will work for right now. All right, so we know that we start off with all kinetic energy. Right, this has all kinetic. And down here we have a different kinetic energy. Let's call it KE1. Okay. Work must be equal to the change in kinetic energy, which will be KE1 minus KE0. No, it wouldn't be potential because we're not going, well, sorry, it's not gravitational potential because we're not going up and down. We're not changing height at all. And it won't be a spring one, a PES, because there's no spring involved here. It's just strictly, we have kinetic energy and we're going to lose it. It's going to be taken away because of friction in there. Okay. And this must be equal to the force of friction times x, the distance we traveled. Okay. So we're trying to find mu here. So this will be 1/2 m v1 squared minus 1/2 m v0 squared equals mu mg x. And now all we have to really do here is solve for x, where you're talking about, solve for mu. So this will be m v1 squared minus v2 squared all over, actually, m's disappeared, don't they? Yep, no m's. v1 squared minus v2 squared over gx over 2gx will equal mu. And there is my coefficient of friction for that particular rough surface. So we started with masses and velocities, and we used that to find energy, and then we did work to get energy, or we did change in energy to get work, which got us to forces, which got us to friction. Okay. And then you may see a question like this. Well, what happens if we make mu bigger? What's going to happen to our final velocity, or something like that, if they're trying to justify and explain sort of stuff like that. So that is all possible sort of stuff there. But there's the derivation for it. So when an object is not moving vertically, there won't be any potential energy. There won't be any change in potential energy. Okay. So potential energy, we're really looking at two possibilities here, right? We have PEG or we have PES. And because we can define our 0 point anywhere we want to for these things, really, I am not going to use potential energy unless there's a change in height, or they specifically mention some sort of spring or something like that. So if I am just moving horizontally, I will say PEG, nope. PES, nope. Kinetic energy, yes. If I have something moving upwards, then I will do PEG. I will do not PES, and then I will have kinetic energy as well, going upwards in there. So those are kind of the options. The only time I'm going to use a spring is if it's actually like harmonic motion or something where you have a mass on a spring, then we can do PEG. Nope, because we're not going up and down. PES, yes, because we have a spring. Kinetic energy, yes, because it works there. And then finally, if I take that spring and I make it go vertically, now we have all three. And we'll do all three types of energy there. Because we're doing vertically, we're changing height, so PEG. We have a spring, so PES, and we're moving, so we have KE. That sort of stuff. Okay. Yeah. So hopefully it helped. I am really interested in looking at that, going deeper into that AP1 question off the YouTube stream. I will do that. And then next week, I think we'll lead off with that one and just clarify that a bit more. Actually, I'll watch through all the streams. We'll just clarify those questions as well. If you guys have other questions or concerns or stuff you want to see me do in next week's stream, here's my email. If you could shoot me either sample questions you're not sure about or topics or stuff like that, or just questions you have, we'll put together some sort of master Q&A test questions, sort of thing like that going on in there. So that will come up in the future. Other than that, thank you guys for a good stream. And yeah, I will see you guys in a week. All right. Have a great day, guys.